Myself Pooja Sharma. I'm assistant professor in computer science engineering department in Ajay Kumar Garg Engineering College. In today's lecture, we will discuss about the intermediate code generation in compiler design. So, the intermediate code generation, it is the final phase of the compiler front end. And what is the goal of intermediate code generation? Translate the program into the format expected by the compiler backend phase. In typical compilers, followed by intermediate code optimization and machine code generation. So, why we use intermediate representation? We use intermediate code representation to make optimization easier. Write optimization method only for the intermediate representation. The intermediate representation can be directly interpreted. Suppose there are four source language. These are the four source language, and we have to convert these source language program into that target machine code. So this is very complex situation when we directly convert the source language program into target machine program. So, with the help of intermediate code, firstly, source language program convert into intermediate code, and then intermediate code optimizer convert that code into target machine code. So, how to choose the intermediate representation? It should be easy to translate the source program to the intermediate representation. It should be easy to translate the intermediate representation to the machine code. The intermediate representation should be suitable for optimization. It should be neither too high level or nor too low level. A single compiler can have more than one intermediate code representation. So there are three common intermediate representation. First is graphical intermediate representation, linear intermediate representation, and three address code representation. So in graphical representation, intermediate code representation, parse tree, abstract tree, and that directed or cyclic tree comes into the graphical representation. And in linear representation, non-graphical graphical representation come into linear intermediate code representation. So last is three address state code. Three address code instruction of the form is result equals to operator 1, opcode 1, and operator then opcode 2. Now the position of intermediate code generator. Intermediate code is the interface between front end and back end in a compiler. So parser, then first parser will come, and then static checker, and then intermediate code gen. After that, intermediate code generator generate an intermediate code, and then it will pass to the backend phase, that is code generator phase, and code generator phase will generate a machine code for the intermediate code generation. Now, the variants of syntax tree. This is the first representation of intermediate code generation. Syntax tree is used to create a DAG, that is directed acyclic graph instead of tree for expression. A directed acyclic graph is an AST, abstract syntax tree, with a unique node for each value. It is easy to show the common sub expression and then use that knowledge during code generation. Common sub expression has more than one parent. Suppose in this example, A plus A multiply B minus C plus B minus C, and then D. So A and B, A and B minus C has common sub expressions, and it has more than one parent. Okay, now this is the directed acyclic graph for this example. A plus A multiply B minus C plus B minus C into D. So firstly A will be there, then A we create a leaf node A, then after that B minus C, and B is a left child and C is a right child of minus sorry sorry. Okay. First, A is a leaf node. After that, B minus C. B is a left child of minus node and C is a right child of that node. Okay. After that, A multiply B minus C. A multiply B minus C. Then in this given expression, A is a left child of multiply and B minus C is a right child of that node. So we represent in this form: A is a right child, A is a left child and B minus C is a left child. So after that, this is the final directed acyclic graph representation for this expression. Now the DAG using array. Sorry. Value number method for constructing a node in a DAG: input, label operator, left child and right child. Output operator and left child and right child. Suppose this is an example, I equals to I plus 1, and for this example, this is a DAG for this example. Now this is an array representation of this particular statement. 0 at position 0, ID will be there, then entry for I. This is an identifier. Okay. Then at position 1, number is 10. Suppose 2 at position 2 plus means 0 plus 1. It means position 0 value plus position 1 value. Okay. Then after that, 3 is equals to 0 plus 1. Then equals to 0 plus 1. Sorry, 0 and 1. Okay. Then an algorithm search the array for a node M with label operator left child L and right child R. If there is such a node, return the value number M. If not, create in the array a new node N with label operator left child L and right child R and return its value N. The search for M can be made for efficiently by using k-lace and using a hash function are determine with which list to check. So this is the data structure array for using DAG. Okay, this is a DAG and this is array representation of this particular DAG. Now the three address statement. Three address code is built from two concepts: address and instruction. Instruction basically a statement or operation. At most one operator on the right side of the instruction. And this is the three address code form: x equals to y, op and z. Okay. An address can be identifier on constant, source variable, program name or pointer to the symbol table name, constant in the program, forms or types of three address instruction. First is assignment statement. We can write assignment statement in this form: x equals to y operator z, and assignment instruction x equals to operator y. This is used for unary operators. And copy statement x equals to y, unconditional jump. Unconditional jump, go to L. L is the label name. And conditional jump, if X relational operator, then Y go to L. Relational operator, it may be less than, greater than, equals to, and all. And procedure call, three address code generated for call of the procedure y equals to p. And index assignment x equals to yi and xi equals to y. Address and pointer assignments, x equals to address of y, x equals to star of y, and star of x equals to y. These are the forms and types of three address instructions. Now we have to write a three address code for the block of statements. Suppose there are three statements: int a, int b, a equals to 5 plus 2 into b. So we can write three address statement for this code like this: t naught is a temporary variable, t naught is equals to 5, t2 is equals to 2 into b. After that, a is equals to t naught plus t1. In t naught, 5 value will be in t naught. So a will in a, the result will be in a. Okay. And three address, we have write three address statement for the if statement. Then if a is less than b, then t1, we execute t1. Otherwise, we execute t2 is equals to 0. Okay. Then we have to write three address statement for this code. If a is less than b, if a is less than b, then go to 4. Okay. If a is less than b, if a is less than b, then go to, okay, then t is equals to 0, then go to. Okay, this is condition for else statement, false statement, and this is for true statement. Then go to. Now t1 equals to 1. If a is less than b, suppose a is less than b, it means condition is true. 1, 2, 3 and 4. Condition is true. Then we have to go in fourth position. It means t is equals to 1. ठीक है, तो यहाँ हम क्या लिखेंगे 4. After that t is equals to 0, then go to कहाँ जाना है हमको 5 statement. Then go to 5. Okay. And this is the three address statement code for the if and else statement with condition. If a is less than b and c is less than d, then t1, we execute t1, and otherwise t is equals to 0. If a is then less than b, first we have to check that condition. This is true. This condition is true. Then we have to go on that. Okay. If t a is less than b, then go to 3. ठीक है. If c is less than d, then go to 6. It means t is equals to 1. Okay. And otherwise, if this condition is false, a is not less than B, then we directly go to this statement. We directly go to this statement. We no need to check that condition in that case. Okay. Go to 4. Go to 4. It means t is equals to 0. And then go to 7. Then we exit the if-else statement. Now, instruction in three address code. Assignment instructions, ठीक है, jump statements, functions calling, index copy instruction and pointer assignments. These are the instructions we are used in three address statement. Now, syntax tree versus DAG versus three address code. ASC, basically, abstract syntax tree is the procedure parse tree with the node for most non-terminal symbols removed. Character cyclic graph is an ASC with a unique node for each value. Three address code is a sequence statement of the general form x equals to y operator then z. If a three address statement, there is at most one operator at the right side of the instruction. Example, a plus a multiply b minus c plus b minus c multiply t. So, ASC for this particular example, firstly we design a b minus c plus that node, and after that then a multiply that one, and after that we execute this one and whole. Okay. And we see that in ASC, B minus C and A comes in multiple times, and we design that node multiple times in ASC. Now in DAG, B minus C and A already we execute, we design, and already A, B minus C node, then there is no requirement to generate a new node for that value, that variables. Okay. So this is the DAG for that particular example. Okay. Now a plus a multiply b minus c and b minus c multiply d. So three address statement for that particular example is this: t1 equals to b minus c, ठीक है, and t2 is equals to a multiply t1, ठीक, then t3 is equals to a plus t2, then t4 is equals to b minus c, and b minus c already in t1 multiply d, ठीक, then t5 is equals to t3 plus t4. Now, implementation of three address statement. There are three implementation: quadruple, triple, and indirect. In quadruple, has 4 fields: operator, argument 1, or argument 2, and result. In triple, there are 3 fields, and indirect triple has addition to triple. We use a list of pointer to triples. Okay. Now quadruple has 4 fields: operator and argument 1, argument 2, and result. In off field contain an internal code for the operator. Okay. Then 3 address instruction x equals to, suppose there is a 3 address statement x equals to y plus z is represented by placing plus operator in operator field and y in argument 1 field, z in argument 2 and x in result. So let's take an example. X is equals to b multiply minus c, unary minus c plus b multiply unary minus c. Okay, three address code for that statement. T1 equals to unary minus c, T2 is equals to b multiply c, T3 equals to unary minus c, T4 equals to b multiply T3 and T5 equals to T2 plus T5. Then A is equals to T5. Then we represent that three address statement in quadruple in this form. We design a four field operator, argument 1, argument 2 and result. Okay. First operator is unary minus. Unary minus argument 1 is C. Okay. There is no argument 2, so we now and result will store in T1. Then second operator is multiply and argument 1 is B and argument 2 is T2 and result will store in T2. Okay. Then multiply B, T1 and T2. After that unary minus is an operator and C is an argument 1 and T3 is an result. Is stored in result. Then after that multiply as an operator, B1 is argument 1, B2, T3 is argument 2 and T4 result will store in T4. So we represent that statement in this form plus T2, T4 and T5. T2 is an argument 1, T2 is an argument 2 and result will store in T5. Then A is equals to T5. This is an copy statement. A is equals to T5. We copy the T5 value into A. Then A equals to is an operator. Then argument 1 is T5 and then A is a result. Then equals to T5 and A. Now the next representation is triple. In triple, we have used only three fields: operator, argument 1 and argument 2. Using triple, we refer to the result of an operation X operator Y by its position rather than by an explicit temporary name, that is position 0 suppose. We take same example. Previous example, this is a previous example. A is equals to B multiply minus C plus B multiply minus C. Three address code for that particular example. Okay. Then we represent that three address code in triple in this form. 0 at position 0. At position 0. First, we store unary minus argument 1 C, and that in position 1 we store multiply as an operator, B is an argument 1, T1 as an argument 2. T1 is an argument 2, but we cannot represent T1 in triple. So T1 will come in at position 0. So we write instead of T1 we write 0. Okay, multiply B and 0. Unary minus C and then C. Okay, at position 2. B multiply T3 and T3 at what position? 2 position. So we write multiply B and 2. After that T2 plus T3, T4, T2 at 1 position and T4 at 3 position. So we write plus 1 and 3. These represent the position of that particular instruction. Okay. Then last is A equals to T5. equals to A and then 4. In additional to triple, we use a list of pointers to triple. We take same example. This is an 3 address statement, and indirect triple, we store that instruction in this form. Okay, operator 0, position 0, 1, 2, 3, 4, 5. This position are also stored in list of pointers. Then 35, we use at place of 0, we use 35 and 1, 36, 2, 37, and 38, and 39, and 40. So this is all about the intermediate code representation in compiler design. So thank you so much.